So, yeah, I got 3 degrees here, and my master's and doctorate, I was working at the time. So it was 18 of the happiest years of my life. That's how long it took. So, I want to talk just a little bit about L3 to give you some context of the other things I'm going to talk about. So right now we're number 8 in the defense industry rankings. We have over 67,000 employees. Here in Salt Lake, though, we have about 4,000. Here in Salt Lake, we do the surveillance and reconnaissance communication systems, tactical SATCOM, networking. You can see the different things. We do a lot of support. Looks like the bottom's cut off, so you won't see my fancy graphics at the bottom. But this is one of the graphs that's very interesting. Of those employees, of the 44,300, 52% are less than 5 years there. That's how fast we've been growing over the last while. And you see, again, if you go to 15 years, you're at 82%. So almost everybody's new within the last little while. And of those, 57% of the people are degreed, and you see 61 bachelors, and masters 29, and then some PhDs sprinkled in there. And then we're just down by the airport. So if you, 2200 West, which is just east of the airport, we're on that whole road there now. So our claim to fame, where we began, was with U2. They would fly the U2, it would gather data, it's got some amazing sensors, and it would gather all this data. Then the pilot would have to come down and land and hand magnetic tape to someone. That person would have to take the magnetic tape to someone else, and maybe a week later, they could process the data and figure out what was going on. And so they came to us and said, could you do something to bring this data down wirelessly? And so this was in the late 70s, early 80s. And within a couple of years, we had a data link on there that did hundreds of megabits per second. Okay, and that's in the mid-80s. So if you can imagine that, that's pretty amazing for that time period. And so because of that, that waveform, or that way of bringing the data down, became a standard for all surveillance and reconnaissance platforms. So you start looking now we're on all these manned platforms. We're on the unmanned platforms. So you probably recognize a few of those: Predator, Hunter, Scan Eagle, Global Hawk. And then surface communication programs. You have both sides of things, where you're bringing data down and where you receive the data on the ground. So we build the communication systems for those systems, and then we're in the different SATCOM arena too. This is an interesting one here. This wavebird antenna is actually on a submarine. And it was an airborne antenna, and they turned it upside down and put it on the periscope so it comes up, but now it's a SATCOM antenna for a submarine. So pretty creative work there by some of our engineers. We're also international. There's a variant of this waveform that is in the international arena too. So we're on a lot of the surveillance platforms there. And then one of the things that probably about 10 years ago, maybe a little sooner, but we got into the field of making products. So people could go online, look at the products, and order these products for their systems. One of the main ones was this Rover 4 system. So we had all these communication systems on the platforms with getting surveillance or reconnaissance data, and they said, can you somehow get that to a person on the ground? And so we came up with this Rover system, and now they get direct feeds from these surveillance platforms. And it's saved a bunch of lives, because now you can see what's going on in real time, know what's behind the building you're walking around, if there's a platform in the area. So exciting there. And that's what some of these others, or those versions of that, the SIR over there on that corner. It's the same as the Rover, except it doesn't have the screen, and you can plug it into whatever video system that you have. So a lot of them will have these ARM screens that they use. You can plug the SIR in there and get the same kind of video that you can get on the laptop over here. So talk about a few of the technology development programs that we've had. So over on the phonics system, that's a DARPA program. And what happens in that program is there's a platform in the air that has to move a lot of data. And so they have an optical system and a high-speed RF system. So it's right now hundreds of megabits per second, but could be up into the tens of gigabits per second eventually. But right now it's just hundreds of megabits in the RF. And then in the optical, it's several gigabits per second. But the optical has issues. If you get clouds or different obstructions, then the signal gets blocked and you can't send down that pipe. And so this DARPA program, we set up an automatic way for the system to detect when that pipe is blocked and reroute over the RF system or repoint to a different platform that has clear view of each other, so the optical system will work. And all of that happens automatically. And so that was a tremendous success. We just demoed that probably 2 months ago. So those are the types of technology type developments that we do. It's more of the networking system. We are doing some things with DARPA on cooling that we were discussing just before this meeting. What other kinds of things? RF and antennas. We do a lot of creative work there that's funded by research and development funds outside of L3. And then we have a very aggressive internal research and development program too. So these are the charts that, when they go out and brief us, describe engineering at L3. So world-class signal processing capability. Most of us taught by Dr. Matthews. Where are you, Dr. Matthews? There. That's why we're world-class. Of course. Decades of experience. I told you we put that first platform up in the early 80s. So since then, we've been on working these platforms. So we're very good at system engineering. And then the field of cognitive airborne network, I talked to you about that. So we have versions of that work for RF networks, for RF optical hybrid networks, and then just the idea of systems work. One of the things you really need to understand as you go out into industry or even as you're doing research is, even if you're working on the smallest component, a nano component, it's always going to be part of a system. And you've got to understand the system view of things as well as the component view if you want to be good at what you're doing. And then capabilities, communications. You see the different things there. You'll probably run into some of the research you're doing here. RF and mechanical, and then networking and software. Okay. We have excellent lab facilities, EMI chamber, antenna ranges. We have manufacturing capability. That's the one thing that I appreciated the most working at L3 is I would do the algorithms to start with, and then I would watch that go all the way into, say, a rover system and watch that work. Where some places you do your research and you throw it over the wall and hope it works somewhere sometime, but you never get to see that. At L3 you get to see that happen. You get to see your things fielded. So you got circuit card assembly, everything you need to do to make a system work we have down by the airport there. And then the other thing that you'll find that's very different than when I went to school, there was a lot more pure research dollars, where you could just go try some things and it didn't really have to fit anywhere necessarily. And that's not the case so much anymore. Now people want to see some demonstrations. Isn't that true? And so we have a very good demonstration team. We go to the customers, they tell us what they need, we do a rapid development and demonstrate and then integrate it into our products. And so here's the key components that you need to make that happen. So the system engineers, you need some demo assets, something that you can grab quickly. And then the platform and the sites, we have an airplane out in Bountiful that we rent, and the guy actually lets us cut holes in it and put our stuff in there. It's kind of fun. So I don't know if he doesn't charge that much either, too, for us doing what we do with his plane. And so tons of demos that are real exciting. And so here's what we've used. I showed you how fast we've grown, and here's the strategy we've always used to do that. So it's a very successful strategy. Deliver on your promises, expand market reach, and give good technical solutions. So over on the relationship side, and then the capabilities you see there, that demo on the right side, that was with some rover products. If you look at the mountains here and the mountains in, say, Pakistan, they're pretty similar. So if things work well in one place, they probably do okay in another place that's similar. Again, our product line control, making sure that we're keeping up with the technology on those products that we deliver, and then a very aggressive R&D approach to things too. So, here's my blatant advertisement here. Go apply. If you look right here, we are seeking junior, senior, or graduate level students. Okay. Now, from there, I want to branch out into the information that we use to come up with our technology roadmaps and the things that apply to what we do. So the DoD has a science and technology focus areas that they've put out. And everything that we're doing right now, our research and development projects are evaluated against these criteria. Tell me how it's going to help me here. And it's got to be in one of those areas. And so I'm going to talk about a few of those areas, but you can see that's where it's going. If you want Department of Defense funding, it's going to be in one of those areas. It's got to be applicable there. So, and then you look at each of the branches. We do a lot of work with the Air Force. So here's the Air Force Science and Technology vision. Create compelling aerospace and cyber capabilities for precise and reliable global vigilance, reaching power for our nation. But the key, you just look at some of the projects they have. So autonomous systems, robust situation awareness, sensing and challenges. So you start seeing the flavor of what people are looking for out there. And I love this terminology that they use. It's called spectrum dominance and cybersecurity. A lot of money in those areas in the research and development. So you see the motherhood and apple pie on the left side here. Information superiority allows friendly forces to collect, control, exploit, and defend information without effective opposition. It means you can move your data around. Okay, so again, we at L3 have been moving data around for a lot of decades. And our systems are anti-jam, which means if someone tries to disrupt the information flow, we've got ways to defeat that. There's LPD, we can transmit data without being detected. Or LPI, which means if it is detected, they can't exploit it. It's got protection. And you've seen that a little bit in the computer world with your bank account information. It's encrypted. So you hope that's good enough that somebody can't get your information out that's critical. Well, that's the same here. And you look now, when we first started, the communications were YouTube, ground. And that was it. That's the only pipe we had to worry about. But I showed you pictures of all the different platforms that are out there now that are moving data. And you get situations like this where you can network all those platforms together. And then from the user standpoint, what they want is it to look like your internet. So I'm standing in a place somewhere in the world, and I want to know what's happening, let's say, a mile away. So I should be able to do some form of a Google search and say, tell me what's happening a mile away. They flow the data down to me that's pertinent. And I really shouldn't have to know what platforms are out there or what's going on. But the system has to take care of all those types of things. And that's where we're heading. But then there's issues that come up in terms of this information superiority. There's issues with bandwidth. With all those platforms flying, how do you make sure they don't jam each other? How do you make sure that the system is secure, that no one can get in and mess things up, provide information that's false, those kinds of things. And so you see the flavor of what's happening in this. So the pillars of this information superiority are to be able to sense, utilize, deny, and manage. And in a sense, you can think about that in terms of spectrum. If I can sense where there's available spectrum, where it's not being used, and then migrate to that spectrum, they're doing that in the cell phone world too, the white space types of research. Utilize, so how do I communicate to other participants in the system that we're all going to move to different frequencies? Deny means somebody's trying to talk somewhere else. I don't want to let them do that. So my superiority is I want to talk, I don't want them to do it. And then manage. And you just see the flavor of what's happening there. So here's some examples of some DoD projects. Affordable laser, behavioral learning for adaptive electronic warfare. DARPA program there. You can see the flavor of what people are trying to do this dynamic and the dominance to the electromagnetic spectrum. So pieces that we have at L3 that are critical to this is we have extremely wideband software-defined radios. We went to FPGA-based radios very early in the game, at the point where FPGAs were just starting to be viable. And so we've got years and years of experience with the FPGA development. And so that gives us a lot of capability in terms of software radios, because to change the dynamics or the waveform that's being processed in our radio, we just have to go program an FPGA. Extremely wideband tunable RF. So control RF front end from tens of megahertz to tens of gigahertz. So in the sense where you say, I can sense some spectrum available here, we can actually slew our system and start using that spectrum. We can use whatever waveform needs to be used to be in that bandwidth. And then I talked to you a little bit about cognitive networking that we have that automatically would switch which pipe you were sending the data down in the RF, hybrid RF optical waveform. So we are working architectures there to do more of that with the software-defined radios. So you see the flavor right here of what needs to happen. You've got the antenna and the RF system, and then across the next wave, it could be any of these applications. And if your processing unit is good enough, you can actually do all of those with the same hardware. And then you need the cognitive agent. And then here you have the sensor packages, strike packages, and the mission platform control system. And so I'll talk a little more about all of these. But so again, here's the software radio-based waveform processing. Single module, lots of different ways to do things just by reprogramming the FPGAs and the programmable devices inside. So now, though, what I would say, our cognitive system right now is probably, I classify it as toddler cognitive, not mature. It does some things really well, and there's a few things it does that have really bought the warfighters some capability, but it's got to go farther. And that's where a lot of research is going to be done. And it's got to be scalable, because somebody on the ground can only carry so much weight versus a ground station, which can have lots of equipment, or something flying on a UAV. So all of these things have to scale to the size and processing capability of whatever platform you want to put it on. It has to be mobile, and again, you see the flavor of the different things that need to go on. So you want it to work something like this. I mean, if we could meet those power numbers, it would be great, but so these are the challenges that are coming up that are forcing this cognitive area to be more important to the warfighters. So you've got manpower efficiencies that are required. They're cutting back in the military now. There's not going to be as many people to run the different systems. Harsh environments where people typically don't want to be. And then the new mission requirements. So again, if we did things correctly, our system is such that the cognitive agent could actually contact the radio, tell it to reconfigure itself to be such and such a radio, and then do such and such a mission. And it would have to sense also and say, what capabilities do you have as a radio? Can you be a hub? Or are you a spoke? Something that's more, can you relay or not? You know, are you just an edge user and you can send data back, but you can't do any of the functions? So all of the nodes would have to have the ability to respond to this cognitive agent, to tell it what they can do, what they can't do, and then to execute those commands. So you see some of the technical challenges. Machine reasoning and intelligence, and then the interaction and collaboration, scalable teaming of autonomous systems, and the one that's going to really be tough, anybody that's ever worked with the government, is test and evaluation and verification and validation. How do you prove to them that what you've got really does what you're telling them it does? One of the ways you can do that, and that's something else we're very, very good at, is simulation. So let's say, for example, I had a network like I showed before of the planes flying, and say there's 20 nodes, hypothetically. The chances anywhere, anytime, I can get 20 nodes to test something are about 0. Right? I mean, I'm just not going to get 20 of those platforms in one place to test unless something bad's happening and I really need it. And so I might get 3, 4, 5 of those platforms in one place. Or I might be able to simulate having more platforms by using our plane down in Bountiful and having somebody driving on the freeway. We do that all the time too. We put somebody up on a hill and fly the plane over here and drive somebody over here, and we see how well the thing works. But this step right here is going to be critical and important. And so in this simulation, we can actually put hardware in the loop, and we can simulate all these planes flying and the data flows that are going on in the network. And the actual hardware and software that's going to run on that platform is running on the system in the simulation. And I think that's the only way you're ever going to be able to simulate and test out these systems. Okay? And again, you have to know the right place to use your tool. There's a saying that says to someone who's good with a hammer, everything is a nail. That doesn't work well sometimes. Sometimes you need some other tool besides the hammer, and if you use the hammer, it's not going to work very well. And so the sweet spot, if you look right there, is you have here representation, fidelity within the model. So how good your model is of reality. So this is for your cognitive agent. This is how well it really knows what's going on versus the knowledge of the environment. So here's your model, and here's what actually is happening based on your sensor telling you what's happening. And then the sweet spot is reality is known and proper reaction is known. Then everything works, right? Because you have the right environment, you know exactly what to do when you're in that environment, boom, it works. Now you get these other quadrants though, where you're probably going to have human interaction in the system. I don't know what's happening, or I don't know what to do with this information, or I need this other piece of data before I can do something. And so you see the flavor. It's never going to be autonomous in the sense that there will not need to be human interaction ever. And again, here's the range of autonomy. So right here with the predator, does anybody know how the predator works, where the pilot sits?
In a control station.
Sits in an office, yeah. Sits in somewhere in Nevada, and they have sticks and they drive the predator. So that's on one end of autonomy. It is flying by itself. There's no pilot, but it's being piloted from afar. And then you go all the way to full autonomy, which is integration of artificial intelligence with human cognitive models. And you see the flavor of what has to happen. So this is human interaction divided by automation is greater than 1 on this side. There's a lot more human interaction going on. And down on that other side, it's less than 1. Just a little bit of human interaction, a lot of machine decisions being made. And it's going to have to move that way. So that sets up now, you've got this idea that there needs to be some kind of cognition on the system running it. Now, what does the cognition need as input? Well, this data to decisions technology assessment is one of the most critical functions. So there are, I don't even know how to describe it, how much information is flowing out there on video, on text, on phone calls, on all the different information that's flowing out there in the environment. Some of it being detected, some of it being fed into a processing location. So here I am now trying to figure out what do I do, or my cognitive agent's trying to figure out what to do based on all this data flowing in. So we were talking earlier, there's a program here in research where they do sensing of biological agents, right? So that sensor feeds some data into this great big mass of data saying, I detected this. And if this is nuclear types of things, that probably triggers something really big that goes up, and data starts flowing like crazy over the network to the different places based on what they see. And so that's what the data to decision is how do you take all this data coming in, put priorities on it, and also making sure you match delay to importance of the data. So this shows you a little bit of how you would think of that. In a tactical operation, you don't have much time to think about things. Narrow field of view, automatic target recognition, and it's megabytes to gigabytes, right? So not a lot of data necessary to make a decision, but it has to be fast. And then on operations intelligence, medium latency, gigabytes to terabytes. And then on strategic intelligence, you're in petabytes. You just start seeing this mass of data that's there. How do you process that? How do you make sense of it? How do you correlate it? And so a lot of research going in this area. Here's some hardware infrastructure. You've got to have the storage, tightly coupled data and algorithms. See, you can't store it all. You're going to have to toss some of the things that are coming in. So how do you prioritize? How do you keep what's good, throw away what's not necessary? Then you have the grid cluster where your storage is out in different locations, and then you go into the cloud computing where you bring all the data together. And again, you just can imagine the massive data that comes in on the cloud. So, dynamic spectrum management has that flavor to it. You've got the way it's mapped out in terms of who owns the spectrum, the TV channel, the cable channel, the phone, and you're looking for the places where the spectrum is available. And again, you can see where D2D comes into play. It's not just a sensing kinds of thing. You say, okay, I'm going to sense this spectrum. It looks like it's available. But then you're going to have to feed in data from other places saying, well, who owns it? What's the chance that I can get to it and use it without causing problems?
Do you really care about that in a tactical environment, though?
No, actually in a tactical you don't. Yeah. So it depends, again, what you're saying is the cognition or the policies that you put on the system. If you're in tactical mode and they know that, so all of a sudden you've got priority, you'll actually go into a place and just stomp on who's ever there. It just doesn't matter at that point. Exactly right. So, simplified view of this spectrum dominance. We have cognitive radio and cognitive jammer and this ability to adapt, learn, sense cycle. With all this data coming in, all these decisions being made. And then here's the idea of the cognitive network management. So, back to the comment here, you somehow, before you can field this cognitive agent, there's going to be some type of policy definition that you put on top of that system. And it's going to have to be tested, validated, right? And under certain conditions, certain things can happen. Under other conditions, they can't. There are certain priorities, certain overrides that can happen. And this is just an example of some of the places where these cognitive systems are under development. But here's some of the research areas. The ability to manage, sense, attack, and communicate simultaneously. So if I'm jamming, for example, I can't communicate in that same place unless I do something creative. So how can I do both at the same time? The ability to draw from shared enterprise knowledge base, so I talked about that, data to decisions. The ability to perform distributed functions. Let's say I have a radio that can put out so much power, but it's not enough, say, to reach a geo satellite. But if 3 or 4 of us maybe can work to gang up our power, then I can communicate using that joint distribution of power, right? So it's being able to pull functions together and do distributed types of things. They do that somewhat in video games now, where they have the cloud that does the rendering and the processing of the images, and it pushes it out to the game player. Because the game player, if it tries to have that much processing power, it's going to be too big, hot, power hungry. And so cloud computing has that flavor to it, where you do the function where you can do it, or you gang up to do a function. One node does part of it, another node does part of it, and they come together to make the whole thing happen. So a lot of research in those areas. So this is an interesting one. You can't see that very well, but there's a web page you can go to see this demonstration, where this robot that they built, it goes around the building, it figures out what doors are open, what doors are locked. It goes into the different rooms and figures out where the plugs are, and then it plugs itself in to charge up. And in this demonstration, it finds, I think they were trying to find 11 or 12 plugs to plug into. You see it plugging itself in, and it does. It finds, and so that was a demonstration of this cognitive type of adaptation. So you can see the flavor of what has to happen to make it happen. So how and when to act, what we know, the facts, and then the previous experience, and based on those things, the machine learns, or the system learns. And it does what it needs to do to accomplish its purposes, I guess. So you're going to feed into the system, here's your purpose, and then the system, if you do this correctly, learns how to make that purpose happen. And it learns how to measure and make sense of the facts that are coming back to it. So here you have the procedural memory, the semantic memory, episodic memory, and then the working memory. And all those are part of what we do. There's habitual versus responding and learning to a new situation. And that's the flavor. So if you looked at that, I wish I could click on it, but I don't have a connection right now. So then the next phase, so you want this spectral dominance, but then the other hand that goes with that is cybersecurity. And you look here, here's the different problem statements that they have. So you can have inside or outside types of cyber attacks. So what's the resiliency of your system, the agility of your system, how well do you know that your mission has been performed? So I did something, I typed something in and said, go do this. Did that command go through? Is it being executed? Are all the things happening that are supposed to happen via the network? And then the one right there is the chip. It's lack of trustworthiness even on the devices. And so all those things come into play in this idea of cybersecurity. And here's the desired end states. You can see the flavor of being able to counter these attacks as they happen. A lot of research dollars going into this area, by the way. So here's the 4 major 10-year objectives that are there. Trust, establish known degree of assurance. The devices, networks, cyber-dependent functions perform as expected. So that's at every level. So you're at the chip level, the board level, the chassis level, and then all the way up into the operational level, that you can trust everything that's going on. The resiliency, again, being able to figure out what nodes are not performing properly or being, how do I say it, compromised, and you're able to isolate those and change the system to adapt. And then the others you can see there, but go through each of these real quickly. So technical challenges on the trust level. You see the flavor of where the research is in terms of being able to verify that the devices you're getting are trustworthy. We had a video that they showed where they have devices that are being washed in a river and then repainted, and then they send them to us. You know, they're the counterfeit parts. But counterfeit's one thing, but the other is, could I put something in the device that comes back and does something to my system at some time? Okay. And then I put some pictures of some of the systems we have on the resiliency. You have the application or the function you're trying to accomplish at the big level in terms of communication for us. And then you drop down and you see, okay, well, inside that communication function, we sit inside a platform, and then inside that platform is our communication, and then inside our boxes are the boards and the devices. And the resiliency has to cover all those. If the device isn't working, I need to be able to sense that and make my device work properly, my communication system, the platform, and then the whole mission. And so everything has to be looked at in that context, that there's every level has to be able to do its part. And this is the assuring effective missions. So again, being able to tell when some part of the mission has been compromised and adjust to that. So what's the dependencies and the techniques for analyzing, being able to discover those things, and then being able to react to those things. And then the last one is the agile operations, being able to reroute or readjust to what's happening. And then you can see right here, once you go into this cyber agility, you're going to have the autonomous control again happening. So can you see the amount of research? And it's again, at every level, there's research going into this area. So, summary, you know, there's the DoD, if you're going to get funding from them, you've got to tie into one of these science and technology areas. And that's where things are going right now. In fact, our chief technologist of L3 Corporation just got done meeting with the assistant secretary of the DoD to go through. He had our major IRAD charts across the corporation, and he went in and showed how each of those fed into that plan. So, any of these?
Well, we're not going to have any complaints. Thank you very much. For our speaker. Questions 1, questions 2. He's going to read all your resumes. So, how do you see this going? I mean, do you see the trend going more and more and more things come your way?
Yes, and the reason why is, let me tell you why we're so successful. I showed you all the platforms we're on. Well, there's no money to put new things on the platforms. So they got to make the things that they have work better. And we did the smart thing in the beginning and going programmable. And so that's paid us well.
What is the future you see with sequestration underway? Well, potential for sequestration underway.
It could be a mess. I mean, yeah, they've got to figure things out. But the bottom line is the one thing they're mandated to do is the defense. Right, and surveillance and reconnaissance right now is a key component of that. So, I mean, if they're going to give, it's going to get ugly, but this is a place where they can't take away too much, if that makes sense. It's like the U2, they tried to grandfather that about 5 years ago, and they couldn't replace it with anything that had sufficient capability, and so now it's good until 2035. Yeah. That's kind of good news, bad news in a sense, you know.
Any other questions for our speaker? But if not, Randy will be here for a few more minutes while he packs up, so feel free to approach him. Thank you again.